Good afternoon. My name is Francisco Molinares,
My name is William Rosado.
and we're Team 21. We designed a diffuser to optimize flow in a hydroelectric system that would theoretically improve the power output. So essentially, a quarter of the world doesn't have access to electricity, and building infrastructure to get to places like the Amazon is very costly and very detrimental to the environment. So people in those communities tend to harvest rainwater to pretty much live, consume, they boil it down to use it for everyday life. And instead of just using it for that, we would also like to, in the process, implement a hydroelectric system and using our diffuser improve the efficiency of the system so that they have at least a little bit of electricity to work with.
Our program statement would be this, to design and test a water diffuser for an hydroelectric system in order to optimize the power on the water turbine.
So our main motivation for this project was FIU has a green kiosk out in the back, and they were designing a hydroelectric system for it. We wanted to be able to contribute a small portion of that project and actually make it more efficient. The purpose of that was just to be able to charge your phone or the laptop, and since the school was giving us so much already, we decided that we wanted to give back. The other major thing that we wanted to do is that designing something from scratch using really advanced theory is a great way to learn how to actually apply what we learned in school in the real world. And our goals for the project were to just increase pressure output by 5% before it hits the turbine, and to also make it relatively inexpensive. Essentially, our biggest concern for this project was the entry length for our diffuser. Since we used the green kiosk here at FIU as our baseline, we only had about 5 feet of height to work with. And based on our calculations, we realized that we needed about 2.9 feet for entrance length for our inlet to the diffuser, which proves a pretty big problem because we pretty much ate up almost our entire length. So we were concerned at that point that we weren't going to have pretty much enough length to see any noticeable change.
Okay, here we present some of the standards that were used on this project. Like in case that we were using a scale 40 PVC, it could be scale 40, scale 80, or 120. Also the standard that relates the pressure on the PVC device. Also the health effects that could have this type of materials, and on a specific standard that takes care of the joints or coupling that is going to be used on the system.
So at the beginning we had 2 designs. We first wanted to just use a 1-inch pipe from the holding tank of the water, which was the initial design criteria we were given, and make it to a 1.5-inch pipe just using a coupling. After some quick research, we kind of realized it's a horrible idea because we would have huge losses because of the ridiculously fast expansion and the fact that we would be essentially just running water, crashing into a coupling, and then expanding. So we decided that we wanted to use a diffuser to do this. However, the diffuser that we wanted to make wasn't something that was readily available, so we had to actually build it from the ground up. And we decided that instead of using PVC and milling it out, which would cost a long time in terms of machining, we would 3D print it, since that's something that seems to be up and coming, and in the end actually works out really well. So our prototype, all we needed to do was increase static pressure once it left the diffuser, and like we said earlier, we chose PVC because it was so inexpensive and so easy to build and tear down that it would help even the most inexperienced person put the system together with almost no tools at all. Once we calculated the velocity profile of the fluid or of the water flowing in the pipe, we pretty much knocked all the numbers out. We used the Darcy-Weisbach equation, and we used the Moody chart to be able to calculate our friction factor and our friction loss due to the velocity profile. And the longer the system is, if the system wouldn't be constrained to 5 feet, the more friction losses we would experience. And since we're cutting the 1-inch pipe portions to the shortest possible length, we would have greater increase in pressure and less losses at the end of the system if we had, for example, a 50-foot system instead of a 5-foot system. So our outlook for growing is great. As I said before, we pretty much crunched the numbers for our entrance length. Then once we did that, we used several theorems to calculate turbulent flow profiles inside of a diffuser, and once we calculated that a diffuser needs to be about 6 inches long, the other length of the pipe was pretty much calculated on its own. The biggest concern that we had with our diffuser was that we don't want any wall separation of the fluid. If that occurs, you can have things like stalling, and essentially we're doing nothing or actually making it worse, because then you have an even greater loss of pressure if you just had a straight pipe going through. And after we ran Flow Express CFD using SolidWorks, we came to the realization that we actually had a very nice profile inside of our diffuser and really didn't have to worry about that. As far as structurally, once we calculated the numbers, we kind of used the theoretical side of things to impose our constraints and to impose the expected pressure inside the diffuser, since that technically would be the weakest part of the system, and we only experienced about 93 psi of internal loading. This PVC specifically is rated for, I believe, 150 psi, or sorry, for 400 psi. So that's well beyond, anything we were going to encounter. And ABS is actually rated to, I believe, somewhere around like 300 psi. It's a range depending on the material and how you've treated it in the whole process. So we're well beyond any concerns with that.
Yes, in order to connect the diffuser to the two different diameters PVC pipes, we're gonna need to use, in this case, certain couplings, PVC cements, and some bushings. The only problem here is that this type of accessories have advantage and disadvantage. In case of the advantage, it allows you to connect different diameters when it comes to pipes, and it creates a very good seal on the system. Whereas the disadvantage is that it does affect the flow of that is entering the accessory, and also the pressure and speed. Here we have all the parts that were used on the system. We have the 1 inch, 1.5 inch PVC pipe, both couplings, the PVC cement, and the custom diffuser. Except for the custom diffuser, all the parts we were able to obtain at Home Depot at a really low price. But in the case of the custom diffuser, what we did was a 3D printer here at the FIU. Here we are presenting what we have for the assembly when it comes to the testing of the device, where we use a plastic bucket. Here we use a bushing plus one inch extension PVC pipe, and the 1 inch PVC pipe ball that is going to be used in order to control the testing process. Here we have the entire system already assembled, and here we have the diffuser. What we did was to fill up the top bucket with water. We position another bucket on the bottom, and when we open the valve, we're going to measure here, once that the top bucket is empty, we're going to measure here the height of the water and the time that it took for the system to fill out the bucket. Here we have the 10 different measurements that we did, where we measured the time, the height of the water on the bottom bucket, and with these numbers we were able to calculate the volume, the flow rate of the system, and the average and the standard deviation.
Using the following equations, we use that test data that we obtained to actually compare our theoretical and experimental results. And as you can see, we were fairly close to our theoretical. We have a slight difference, about 1%, and I would attribute it to more of human error, because we had we had some leaking in our system. We also had hand timing how the flow rate was coming. So a lot of those numbers are pretty much subject to a lot of variance and standard deviation. And if you look at the chart we showed before, we had standard deviation about 1.3. So that's significant. If we had a more controlled environment, we'd probably be able to get a significantly closer number and not have this slight variation. However, compared to the baseline design, which was just a 1 inch pipe from the water source to the turbine, we managed to increase static pressure by 3% compared to our experimental results, which may not seem like much, but in correlation with static pressure and the power output of the turbine, this would roughly give us about a 3% increase. So if we had nothing before, we wouldn't have gained anything, and we managed to improve the system by adding a $60 diffuser, which if you mass produce it, would be significantly cheaper.
In case of the maintenance, we will have two possible process for the maintenance. The first one is going to be shutting off the bulb that is going to get water from the tank, from the regulation tank or whatever deposit we're going to have on the top. Then we're going to remove the pipe, the top pipe from that valve, and we're going to apply some peroxide, like between 3 to 9 ounces of that cleaning system. And then we're gonna let the system run like for about 20 minutes, and then clean out the system and put it back to the initial position. The second one that we have is that we can close the valve, remove the end top, the finish of the pipeline. We're gonna put a vacuum and we're gonna apply like a 30-second process in order to remove every possible clog on the system.
So the global impact that our design would have is that hydroelectric systems already exist. We don't want to reinvent the wheel, but we want to squeeze out as much juice as we can from these systems. The target audience for this would be someone who does not have access or is readily accessible with electricity. So any more power that they can pull out of their existing system would be fantastic for them. It just means, you know, maybe they can run something a little bit longer, or they can do any small thing that to us seems, you know, meaningless, but to them means the world, because they don't live in the same world that we live in. We also like to be able to contribute to the up-and-coming, you know, electric green energy field. And you know, with this, we're kind of proving that this concept, if applied to a more massive scale, would actually improve the efficiency of these systems and improve and increase the likelihood that they could be applied in other places. And I mean, it may not seem like much, but I think adding something to FIU also improves and, you know, makes an impact, because we're all from different places and we all, you know, see different things.
Here we're presenting like a table where we show all the labor that it took to accomplish the entire project, like that, you know, 50, 75, 100% of the report, how much we put on every single team member on the entire project, having like a total of 104 hours to accomplish the entire project. In this case, we're presenting the cost, where we have every single accessory for the cost, and we are showing a total price for like $5,000 for, you know, in case that we are doing, you know, a specific, you know, design for only one option of the system.
However, that's not a realistic way to price our system, or actually our diffuser, because we aren't selling the PVC. The PVC is bought anywhere. If you were to scale this up to 50, the PVC add-on would be about $96, including the diffuser. However, when you tend to go to market with things, you don't make 50 of them, you don't make 100, you make a significant amount more. So the more you scale, the cheaper it would significantly become. And in terms of making a profit, this is something that we would want to use as more to better someone's life and not really make money off of it. Because in terms of the U.S., there's a lot better ways of doing this without having to you know, pursue these methods. This is essentially a breakdown of our project in terms of time, and as you can see here, William was the lead designer, researcher, I was team leader and designer/tester.
As a conclusion, we can conclude that the PVC is a really good material when it comes to assembly and disassembly of the system, and also is a perfect material when it comes to the lifetime of the entire system.
In the future, we would like to be able to incorporate an actual turbine into our testing, and the reason for that is that we would like to put fins in our diffuser design so that we could actually start rotating the fluid before it goes into the turbines, and we're hoping that that should also improve the efficiency and the power output of the turbine. And the other thing that I noticed is that many HVAC systems use, for example, 1-inch nominal pipe when they're doing ground heat exchangers. If you were to add a diffuser to the end of that heat exchanger in the ground and it's going into the house, it would actually help reduce the velocity and increase the hang time, and thus the time that the cold fluid or the hot fluid on the floor could mix with the air in the actual heat exchanger, causing a better efficiency for that system.
We have some of the reference that were used normally for the PowerPoints for the entire project also. Do you have any questions?
have one question, if you don't mind, before looking at your report here, your project timeline is only this semester. Yeah, you guys done this in one semester?
Yeah, so the original project was supposed to be a diffuser and a turbine, and it was supposed to be something like, a previous project had presented something about a stabilization system for the Gulf. So we had originally designed a turbine and the diffuser with it. However, I went on an internship in the fall semester, and we were supposed to continue working on that, but we ended up having issues with communication and between FIU and us, and we decided that instead of causing a headache for everybody and failing miserably, we would pretty much start over. And we had to start from scratch, kind of, but all the research that we had done on diffusers and how they affect flow and stuff like that was still pertinent to our project, so we kind of managed to come up with something. That's why if we would have started when we should have started, I would have liked to have an actual turbine to see what the final values were, but since our timeline was so short, I didn't want to risk not having full information and putting it in a report without having final values.
No, that's understandable. Like I said, I just wanted to check and make sure on that
Yeah.
first.
Can you talk us through, I guess, your thought process for designing that specific diffuser?
So what I did for this project was, in terms of design, I usually look at how my system is going to constrain what I can and can't do. And so what I ended up doing was that based on the height, I knew I was going to have a problem with entrance length. And if I don't have the proper entrance length, my diffuser is utterly useless. So that was pretty much a driving factor in the entire project. Once I managed to get that entrance length to a number that I could deal with in terms of my limited height, then the diffuser design aspect falls under, there's specified charts and equations that you can use, and it allows you to determine the expansion rate and the angles within the diffuser to kind of put you near somewhere where you shouldn't have wall separation, but nothing is promised. That's why we had to run a CFD to make sure, because if not, then we would have pressure loss instead of pressure gain, which would be counterproductive to what we were trying to do. And then once we did that, then the rest was pretty much just fill in the blanks from there.
Do you think if you would have had more data points, you would have had less of an error in there and had more gauge R&R, so you did it the same way
Yeah.
over and over?
The error that we had on the system while we were testing is that we have between 2 to 3 leaks during the system.
Oh.
And besides, we found out that once the level on the top water bucket reached a certain level that was really low, it creates like a certain vacuum inside of the system that would affect the flow on the system.
Multi-phase.
Yeah, so I mean, this all stems from the lack of time. The fact that we had to design everything in February, have it assembled and built in March, and then the first 2 weeks of April, while I wasn't in the state, because I was in California, working at my internship, test is kind of just, we were really like, well, we gotta build something, as long as it flows, it works. We're gonna have error, but it should be hopefully comparable, and it turns out that it actually gives us relatively good numbers. But of course, there's always room for improvement, and there's always ways that we can make things better.
Yeah, I think another interesting thing to point out is all of your pressure readings are done in absolute as opposed to a gauge pressure.
Yeah.
So just be aware of that. I was looking at one of your simulations earlier. I was looking at 92 psi on a 5-foot drop.
Yeah.
And I'm going, wait a second.
Well, because the reason is because the original constraints from the other side of the project is an open tank where the rain collects into the tank. So the atmosphere, the pressure would be atmospheric pressure.
All right.
What size turbine would you use at the end of this crane?
So the turbine was actually being handled by a master's student here at FIU. And as far as I'm concerned, the turbine was supposed to be a vertical, so like the water flows correct me if I'm wrong, Dr. Tremonte, was the turbine supposed to be a vertical turbine, or was it supposed to be an actual wheel where the water hits and it comes out through the sides?
Yes, it's a Francis turbine.
Yeah, so
which is perfect. The inlet flow is actual and the outlet flow is radial.
Yeah,
Yes,
so-
you have a change of direction of 90 degrees.
Yeah, so the actual inlet of the turbine would be 1.5 inches where the water would hit, and then the actual turbine size could be, sized accordingly to how much, I guess, energy you have to move that. But I wouldn't know the specifics of that because I didn't deal with that end of the design.
And that's, like, say, here's a turbine, that's like right here, and then you got the pipe and the tank on top. Or-
It's gonna be, we're gonna have another, like a piece of 1 inch pipe, 1.5 inch pipe after the diffuser.
Okay.
Yeah, so
I'm
it
just
would,
trying to picture it in my mind.
yeah, it would just be essentially the 1 inch pipe from the tank, the diffuser, and then the 1.5 inch pipe to reach the length required, whatever the length may be, to the actual turbine. And then the idea is that since we changed from the 1 inch to the 1.5 inch as early as we could, we're minimizing all the friction losses that we could incur by using the 1 inch pipe longer. So if this system was 100 feet long, we would only be using 3 feet of 1 inch pipe, and then the rest would be 1.5 inch, and that would lower our Reynolds number, which would reduce our actual friction losses. So that would improve the efficiency of the system, which is why if we were to scale this up, it would be a lot better than having such a tight system.
Yeah, unfortunately here we are dealing with low heights,
Right.
3
Yeah.
meters, maybe 10 feet. So the idea of that diffuser is to increase pressure as much as we can. So we can, from one side, increase power and increase efficiency.
Right.
That's the main objective of that diffuser.
You guys mentioned that applying, I think, the collar